Hello everyone, hello Laushi. Today I am going to present LAL linguistically aware learning for syntax recognition. I am MD Munim. My student ID is 201963990164. Okay, then let's talk about the content. The introduction to LAL method architecture of LAL rectifier encoder attention decoder next character prediction model uh, dataset syntax conclusion. Okay, the introduction to LAL. Syntax recognition is the task of recognizing character sequence in image of neural sense. The considerable diversity in the appearance of next in the scene image and potentially highly complex backgrounds make text recognition challenging. Previous approach employ character sequence generator to analyze the text regions and subsequently compare the candidate character sequences against a language model. In this work, we propose a bimodal framework that simultaneously utilizes visual and linguistic information to enhance recognition performance. Our linguistically aware learning LAL method effectively learns visual embeddings using a rectifier encoder and attention decoder approach and linguistic embeddings using a deep next character prediction model. We present an innovative way of combining these two embeddings effectively. Our experiments on 8 standard benchmark show that our method outperforms previous method by large margins, particularly on rotated uh, for short end and curved text. We show that the biomodel approach has a statistically significant impact. We also contribute a new dataset and show robust performance when LAL is combined with a text detector in a pipeline next spotting framework. Okay, the next slide will talk about the method. Syntax recognition is a research program that has attracted significant interest due to its importance to various tasks such as assisting the visually impaired scene understanding or autonomous cars and image retrieval, while optical character recognition techniques works well on printed document images. Syntax recognition remains a challenging problem due to large variations in text appearance, layout, and background. Text, text with convolutional and recurrent neural network recognizing irregular text is more difficult. This includes rotated text that is not horizontally aligned with the image, and for short end text due to perspective projection. Moreover, the text design itself may not be straight but contain character aligned along a curve or have misaligned character. Images of such text design may when we also rotate and foreshortened created without the ability to handle irregular text. The method mentioned above often struggle in recognizably irregular text. Okay, this slide will talk about the agriculture of LAL. Recognizing of irregular text has been addressed by two main lines of research: rectification based and 2D feature map based approach. Rectification based methods adapt a spatial transformer network (STN) to rectify irregular text images into regular shapes and then recognize them with regular text recognizer. 2D feature map based method learn 2D feature maps from the original input image without any rectification and generate characters sequentially in 2D space. For example, the method by check EDAL encodes 2D space information for directions to transform the 2D image feature map to 2D feature sequence. LIETLL proposed a 2D attention mechanism that encodes the 2D feature map column by column to yield a holistic feature vector and then decode this holistic feature vector by applying 2D attention mechanism on the image feature maps. Most state-of-the-art methods use solely visual information to recognize irregular text. A character sequence, however, is designed to convey linguistic information to the observer, and this linguistic information, in addition to visual information, should be utilized. Our approach is therefore to fuse visual and linguistic information inspired by the transformer method, which has made profound advances in solving various tasks in neural language processing. We, we propose a new linguistically aware learning approach that incorporates a transfer based model. The architecture of our biomodel feature learning model for text recognition LAL. It consists of a rectifier, encoder, attention decoder, and a next level prediction NCP model. Okay, in this slide we will talk about the rectifier. To address the non-linear spatial arrangement of a chart characters and perspective distortion issues in scene text images, we included a rectification module as the first component in LAL. The architecture for rectification is inherited by Shi et al. LAL used a 6-layer CNN to predict 20 control points to localize the text on the input image and attempts to rectify the input images to access align from with a thin plate spline approach. Some distortions may still remain to maximize the efficiency of the rectification module. We created a new synthetic training based by modify a widely used public synthetic dataset. Encoder. The encoder processes the rectified image through a 45-layer REST net that captures local patterns and textures followed by two layers of a bidirectional LSTM BILSTM. Each layer consists of a pair of LSTMs with 256 hidden units. The BILSTM captures long-range dependence of the feature sequence in both directions and outputs the new feature sequence where L is the maximum word length, a fixed parameter determined in advance. Okay, so this slide will talk about attention decoder. The decoder retrieves the feature sequences of the encoder to generate a sequence of character. We propose a linguistically aware attentional sequence to sequence model to align target and label. It works iteratively for L step, producing a character sequence of length L denoted by C1 to CL. So the next character prediction model, the input that LAL first passes into NCP is a prediction of the first character of the text O, which LAL makes slowly based on its visual analysis. Give this first character NCP, can the predict a ranked list of characters that most likely follow as the second character of the text. NCP passes an embedding the vector which represents the various choice of the second character to the attention decoder of LAL, where it is combined with visual information to recognize one in the prefix. As more and more characters are given as input, NCP is able to obtain more information about the word and becomes more accurate in predict the next character. So the next slide will talk about dataset synthetics. Supervised training of syntax recognition model based on deep CNNs or RNNs requires a very large number of the label training data sets. These models contain millions of parameters. Not only are inadequate numbers of data insufficient to train deep learning models, they also limit how variations in next font size and position in neural image can be represented. Consequently, two large datasets have been created synthetically and become widely used by researchers to train text recognizer SYN90K. 9 million synthetic dataset generate based on 90K generate English words. It has a large vocabulary but the images are monochrome, so it is used with synthotext provide realistic colored scene image. We found that synthetext has a relative productive or crowd text in instances. Our solution is to use the synthetext generating engine and the same background image along with their segmentation and tape the mask provided by Gupta EL and generate additional realistic curved text images. We refer to enhanced dataset as synthetext. The next slide will talk about the conclusion. Recognition of irregularly shaped text in scene images has been addressed in the computer vision community mostly as a single modality problem processing visual information only. The paper instead proposes the scene text recognition method LAL with an explicit linguistic based approach by utilizing visual and linguistic dependencies through through a self-attention mechanism. LAL is able to sequentially predict characters if the networks in LAL that process visual information struggle to predict correct characters. The network that process linguistic information make up for it. We showed that this effect of biomodality has statistical significance. LAL sets a new bar of estimate of the art performance on the next recognition benchmarks. Archival accuracy levels that are substantially higher than those of previous models, an average of 3.3 percentage points on irregular text database. LAL also shows better performance on the highly challenging TPID than previous methods. The strong performance of our next spotting system LAL when tested on data Hansen to LAL shows that LAL is robust and generalized without any one turning and can be effectively included in two-stage next spotting system. So this is my presentation. Thank you so much.